Okay, everyone, let's get started. Okay, great. So last time we've seen basic calculation of the symmetric group. Today we'll introduce a new group. It's a group that's more or less one of the nicest groups we will see in this course. But before, let us start with some definitions. Let G be a group. A subgroup of G is a non-empty subset H such that one, the identity in G belongs to H. Two, A, B are in H, then A, B, a circle B is in H. And three, if A is in H, then A inverse. Okay? I have a group G. A subgroup is just a non-empty subset of G such that the identity of G belongs to H. If I take the product or the operation of two elements in H, I get back an element in H. And if A belongs to H, then A inverse belongs to H. Okay? Great. Let's give an example. So basically, H will be a group, right? If you have these three properties, H will be a group. You see that? Yeah? H will be group. Okay, let's give an example. Consider the group R plus with addition. Then Z plus and Q with respect to addition are subgroups of R. Okay? So, what's the identity element of addition? 0. Does 0 belong to Z?
Yes.
Now, if A and B belong to Z, then does A plus B belong to Z?
Yes.
Yeah. So that's the third property. Now, that's the second property. Look at the third property. If A belongs to Z, what is the inverse of A under plus? Minus A. If A belongs to Z, then does minus A belong to Z?
Yes.
Yeah. So Z is a subgroup of R. And Q, subgroup of R. Okay? Now, another definition here. A group G circle is Abelian if for all G, H, and G we have G circle H is equal to H circle G. Okay, let's give an example. R plus is Abelian, right? Addition is commutative. The operation is commutative. If you add x and y, or you add y and x, you get the same answer, right or no? R, the non-zero real numbers under multiplication, is also Abelian. Agree? You take the non-zero real numbers, you multiply them together. You multiply A times B, and you multiply B times A, you get the same answer. Well, what's an example of a non-Abelian group? Let's look at matrix groups. GL2, well, GL2R. Is it an Abelian group? So GL2R, remember, it's the set of invertible 2x2 matrices with real entries. We showed that this is a group under multiplication of matrices. You remember? On Monday? The product of two invertible matrices is invertible. Yeah or no? Remember this? Monday? Yes, sir.
Sorry, you might have already mentioned what is Abelian.
Abelian?
Yeah.
If G.
What is Abelian?
Oh, it's this is a definition. It comes from the name of the mathematician Abel.
Oh, okay.
Okay? Abelian, you can say commutative. I'll avoid using commutative because we'll use commutative for something else later on. But it's called an abelian group if for all GH, G times H is H times. Yes, somebody had a question. Yes. Okay. Yeah. So R plus is abelian, and the set of non-zero real numbers is abelian under multiplication. Right? Abelian means the operation is commutative. A circle B is B circle A. Yes?
Why not regular R in multiplication?
Regular R in multiplication. Now, is regular R under multiplication a group?
No.
Does 0 have an inverse?
Oh no.
Okay? Multiplication on R is commutative, yes. But R under multiplication is not a group. To make it a group, you remove 0, and you get an inverse. Oh, yes?
Is it matrix multiplication of the commutative?
Exactly. Is JL2R an abelian group or not? Is matrix multiplication commutative? Matrix multiplication is AB is equal to B times A in general. It's not commutative. It's not abelian. Okay? Abelian means that the operation G times H is H times G. Or G circle H is H circle G. Yes, sir.
Really stupid question. With the r minus 0 and x, isn't 0 its own inverse?
No, it's under multiplication. 0 times 0 is 0. The identity for multiplication is 1.
Oh, okay.
Okay.
Yeah, okay.
0 times anything is 0. So 0 has no inverse in R under multiplication. Okay? Is it clear what abelian means? It's just that the operation commutes. A operation, like A circle B is B circle A. Okay, GL2R is not abelian. What's another non-abelian group? Sn for n bigger or equal to 3 is not abelian. How do you prove that? Could you give me an example of two elements that don't commute? Think simple. Think simple. So let's take the permutation 1, 2. It flips 1 and 2 and fixes everything else. Okay, remember this notation? It flips 1 and 2 and fixes everything else. Yeah? Remember this or not from last time? And let's take the permutation 1, 3. It flips 1, 3, 1 and 3 and fixes everything else. Let's take the product of these two. Let's remember 1, where does 1 go to? What happens to 3 here? Fixed, right? 3, where does 3 go to? 1. And where does 1 go to? Well, 3 goes to 2. Let's check that 2 goes to 1. 2, what happens to 2 here?
6 to 7.
And then here?
1.
So what happened? Alright, what happens here? I close the cycle. Great. And let's start at 1, 3, 1, 2. And you will get 1, 2, 3. Okay? 1 goes to 2, 2 stays fixed. 2 goes to 1, and 1 goes to 3. And then you can close this out. Okay? Are these permutations the same?
They are inverse of one another. But
Well, are they the same? That's the question. Are different. Okay? So Sn is not abelian. For n bigger or equal to. Okay, guys? Are we good here? Yes?
But that's simply because function composition is not
Exactly. That's right.
n equal to it's
N equal to is commutative. You have two bijections for n equal to, right? You don't have that many. So that's right. That's a good question. What is S2? This is the identity function and 1, 2. You have the set of bijection from 1, 2 to 1, 2. How many could you have? You either have the identity or you flip them. Very good question. Yeah. S2 is abelian. S2 is the only, S2 and S1 basically, right? S1 is the bijection from 1 to 1. Yeah. So S2 and S1 are the only abelian groups. Okay? Are we good here? Are the only symmetric groups that are abelian? Yes, sir.
So Sn is like the group of bijective functions.
From 1 to n to 1, yeah. Are we good? Clear? Yes?
So function composition is Abelian?
No, function composite is not commutative, right? If you have two functions, bijective from x to x, what you would expect is that f composed with g is not equal to g composed with x, in general.
Okay, unless it's the inverse.
Well, yeah, could be, unless it's equal to f, for example. G composed with g is equal to, you can flip it, okay? But in general, it's not true. So this group is not abelian. Yes?
Is Sn always the notation for the functions?
Yeah, Sn, we're going to use it now for the bijections from 1 to n to 1 to n. Yeah. Any other question? Great. Okay. Now, the group Z mod NZ and UN, the groups. Okay. Now we're going to slightly deviate from group. This is Z slash NZ and UN. So now let N be an N. We're going to slightly come back to what we've seen before. Let N be an N. We say that A, B, and Z are congruent modulo n. We write this A is congruent to B mod n. If and only if A minus B is divisible by n. We've seen this relation before, right? You remember this? We didn't see the word congruent, but we did define a relation on Z, and we said that A and B are related if the difference is divisible by n. We took n equal 3 as an example. Not so long ago, maybe like a week ago.
Can you re-explain it
Yeah.
quickly?
Sure. Define a relation on Z, A is related to B, if A minus B is divisible by n. This is the first equivalence relation we show, right? That's it. Yeah? Recall? Define relation on Z by saying A is related to B if A minus B is divisible by n. Remember this relation, right? No? We don't remember it? This is the first equivalence relation we showed. Yes?
Just have a question. What is, it's UN? What is
UN. I'll introduce them later. I'm just saying that this is the title of this section. Okay? So let n be an n. We say that A, B, and Z are congruent modulo n. A is congruent to B mod n if and only if A minus B is divisible by n. We remember this relation or not? Yeah, great. So instead of A related to B, I'll just write A is congruent to B on n. Instead of this, I'll write this. That's it. Simple as that. Okay? Great. So congruence mod n is an equivalence relation on Z. Should I prove this again, or it's okay? Should I do it again? I think it's okay. And what are the equivalence classes? So let's give an example. We gave in class the example of n equal 3. We had the equivalence class of 0. What is that? It's the set of x and z such that x is related to 0, right? What is related here? I just replace it by this symbol. Mod 3. This means it's x minus 0 divisible by 3. Yes, sir? It would be 3z. That's right. It's 3 times the multiple of z. You remember this? Yeah? Now what's the other equivalence classes here? Yeah? Go ahead. 1? The equivalence class here? The equivalence class of 1? Yeah? Don't hesitate to participate. It's a good thing. The equivalence class of 1. It's the set of x and z such that x is congruent to 1 mod 3. So what is that? This is 1 plus 3z. Remember this? Everybody, do you remember this? And the equivalence class of 2, what is it?
2 plus.
It's 2 plus 3z. Very good. Right? So let's remember that we say, this is just a notation. A is congruent to B mod n if and only if A minus B is divisible by n. Okay? Great. Now let's remember the properties of equivalence classes. The equivalence class of 5, what is it? The equivalence class of 5.
Wait, no, it's 2 plus 3.
The equivalence class of 5 is 2 plus 3z, right? I mean, it's also 5 plus 3z, right? It's 5 plus 3z, which is equal to 2 plus 3z. Agree? Everybody? Yeah. Great. Okay. Very nice. Now, if n is equal to 5, how many equivalence classes do I have? If n is equal to 5, what are the equivalence classes? How many equivalence classes do I have if n is equal to 5?
5.
5 equivalence classes, yeah? They are? Yeah? Well, it's the class of 0,
Class of 0, class of
the class of 1, very good, the class of 2, the class of 3, the class of 4, that's it. Right? Everybody, are we good? Is it clear? Great. Now what is this? This is 5z. This is 1 plus 5z. This is 2 plus 5z. 3 plus 5z. And 4 plus 5z. Now just a question. The equivalence class of 7, in which one will it lie?
2.
7 will be here. So the equivalence class of 7 is equal to 7 plus 5z, which is equal to 2 plus 5z. Agree or not? Yes or no? Very good. Any question on this? Please ask. Please ask. Basically, you have 5z, and you add 2 to every element in 5. It's the same thing as if you take the multiples of 5 and you add 7 to it. You get the same numbers.
Can you play about like mod 3?
Mod 3. So, mod, like the word mod.
I guess, yeah.
Yeah, the word mod, I think I've Googled it not a long time ago. Modulo means up to. So, A is equal to B, so 5 is equal to 3, up to a multiple of 2, differing by multiple of 2. Right? So it means like 5 is congruent to 3 mod 2. How do you check if this is true? You take 5 minus 3. Is it divisible by 2?
Yeah.
Yeah, so this holds. So 5 minus 3 base, 5 is equal to 3, up to a multiple of 2. This is what mod means.
Okay.
But for us, modulo, I think this is the definition of modulo. But for us, this is just a symbol. A is congruent to B mod 2 if A minus B is divisible by 2. Okay?
Yeah.
Okay. So let's try a small example. 7 is congruent mod 5. Can you put a number here? 2. Very good. Can I put 12? Yeah? Can I put 19? It's not congruent, right? Can I put, well, wait a second. It's not congruent to 19. Is it congruent to 17? Is it congruent to 19? Okay? So you take 7 minus 12. 7, 7, 7. Okay? You take the difference of the 2's. If it's divisible by 5, then it's congruent by 5. Okay? Great. Now let's prove some property about these congruences that are very important. Let's first do a small example. 7 is congruent to 3 mod 4. Agree or not? Yes or no? Let's see. 9, well, let's take, well, I don't want to take that. Mod 4, they're not too many numbers like this. 9 is congruent to 1 mod 4. Agree with these statements? Now 7 plus 9 is equal to 16. Is equal to 0 mod 4. Agree or not? 16 minus 0 is divisible by 4. Yeah? Now, 3 plus 1 is congruent to what mod 4? Equal to 4, which is congruent to 0 mod 4. You've seen this? If I add these two numbers, and I took mod 4, and I add these two numbers and I take them mod 4, I get the same answer. I get the same equivalence class. Right? Okay. Are we good here? Now let's take the product. What is 7 times 9? 63. Mod 4 is what? What is the best number you can get? The nicest number. 63. How much you remove from 63 to get a multiple of 4?
6.
No, how much from 63 do you remove
15?
to get a multiple of 4? No, 3. You remove 3, right? 3 mod 4. Right? And 3 times 1 is congruent to 3, is equal to 3, is congruent to 3 mod 4. Okay. So now we have a small conjecture I think we can prove. If, well, let A, B, C, D be in Z, if A, B, C, D be in Z, and N in N, suppose that A is congruent to B mod N, C is congruent to D mod N, then A plus C is congruent to B plus D mod N, and AC is congruent to BD mod N. Okay? I mean, really, if you want to find a good number, so 63 is congruent to what mod 4? You take the remainder of the Euclidean division of 63 by 4. Right? So for example, if A is equal to N K plus R, then A is congruent to R mod N. Right? Because A minus R would be equal to NK, which is divisible by N. Agree or not? Yeah? Have we seen this before?
Yes.
Okay. So some of you might have seen it, most of you maybe not. Is it clear? Is it clear what modulo is? Modulo is just, you know, you give a number. Usually you pick the remainder. Yeah, any number is congruent to its remainder by the Euclidean division by n. Okay? We'll give some examples later on. Now, how do I show these? How do I show these statements? How do I prove these? What does, yes?
You use the divisibility notation for
I
it.
use the divisibility notation.
Divides n.
Pardon?
A minus b divides n.
N divides A minus B.
Huh?
N divides A minus B.
Oh yeah, sorry,
Yeah.
not n. Yeah. No.
Let's have a look at this. We need to show that A plus C minus B plus D is divisible by n. Now what is A plus C, right? That's what I need to show. To show that the first statement holds, I need to show that A plus C minus B plus D, the difference of these two terms, is divisible by n. Agree or not? Now what is A plus C minus B plus D? A plus C is minus B plus D. Let me write this as A minus B plus C minus D. Agree with this? Everyone? Great. Now, A minus B, is it divisible by n? Why is it divisible by n? By assumption. Because A is congruent to B mod n. This means that A minus B is divisible by n. This is divisible by n. Is this divisible by n?
Yes.
Why?
Because C is congruent to D mod n.
Very good. Are we good with this?
Yes.
Everybody? Yeah?
How would you like write A is equal to B plus everything?
Sure, yeah, we can do that.
Like, so
Yeah, we can do that. We can do that. So, yeah, so, okay, let's write this. Let's write A is equal to B plus K times N. And C is equal to D plus Q times N. Okay? We agree we can write this. A minus B is divisible by K, is divisible by N, and C minus D is divisible by N. Okay, so what is A minus B? A minus B is Kn, and C minus D is Qn. Okay? Which is divisible by N. Is it good? Yeah? Great. Yes?
I got like a really quick question. I think things are being a little bit fast, but like, what was the thought process, like, that you needed to show like A plus B minus B plus D is divisible by n? Where did that come from?
Oh, what is,
Like,
what,
how did that like, how did you know like, that was the first thing that you needed to?
where? I mean here?
No, it's the very first thing.
Oh,
you said
I
you
need to show that A plus D is congruent to B plus D mod n, right?
Yeah.
So what does it mean? It means that A plus C minus B plus D is divisible by n.
Oh, okay. I see.
Yeah.
I see.
Okay, great. So A plus C divisible, this is divisible by n. So A plus C is congruent to B plus D mod n. Now I'll show the product. Let's do the product. We need to show for column 2 that AC minus BD is divisible by n. Okay? A minus B is divisible by n, so I wrote A is equal to B plus Kn. C minus D is divisible by n, so I wrote C is equal to D plus Qn. Now let me replace these here. AC minus BD, what is that equal to? So A is B plus KN, C is D plus QN, minus BD. Great. Let me expand this. It's BD plus N. Okay, what's this? Do it. Take 2 steps to do it. BD plus N plus B QN plus K ND plus K QN squared minus BD. Now notice that the BD will cancel out, and let me factor a common N from here. So the BD will cancel out, then I'll have N times BQ plus KD plus KQN. Is this difference divisible by N? The difference is divisible by N. I get N times something divisible by N. So AC is congruent. Okay? You know, let's give some examples. So if A, this is A, if A is equal to BQ NQ plus R, where 0 Rn, this is the Euclidean division by n, then A is congruent to R on n. Okay? Let's pick an example here. Let's say 66. Let's see mod 4 is equal to what? It's 4 times 16 plus 2. Right? Agree or not? So 64, so 66 is congruent to 2. Okay? That's clear? Yeah? Is it clear? So basically, one way to see it, you take the number, you find the remainder by dividing it by 4. Okay? Are we good here? Everybody? All good? Great. Now, should we do some examples on how to calculate these, or that's okay? It's okay? Let's just do one more example. I don't know. A number? Who volunteers for a number?
7.
4.
11.
11 is good, yeah, 11 is good. I like 11, it never appeared with us. Another number, someone who never participated. You gave 11, no?
62.
Oh, okay, go ahead, yeah. 65. 65 mod 11 is congruent to what?
Minus 1.
It's congruent to minus 1, right? 65 minus minus 1 is 66, which is divisible by 11. Now, it's also congruent to 10 mod 11. Right? 65 minus 10 is 55. Okay? Are we good here? What's the remainder of the Euclidean division of 65 by 11? It's 10. Okay? It's clear? I think that should be okay. Now, what is a good thing? Why are we doing this? The thing is, the set of equivalence class. Now, how many equivalence classes?
10 of them.
Yeah, of equivalence classes of congruence, or of congruence classes we call them. Anyways, of congruence modulo n is a set with how many elements? How many possible remainders you can get by dividing by n? N is a set of n elements that could be represented by, these sets could be represented by the class of 0, right? The class of 1, and the class of 2 mod n. And then the last one is the class of n minus 1 mod n. Agree or not? What are the possible remainders you can get when you divide by n? 0, 1, 2, blah, 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 n minus 1. Okay, if I tell you the equivalence class of n, where do you find it? The equivalence class of n, where do you find it? 0. The equivalence class of n plus 1. The equivalence class of n plus n. The equivalence class of n plus n, where do you find it? Great, awesome. Okay, it's a set of n elements. Well, why did I write it this way? I don't know why I wrote it this way. 0, 1 modulo n, and n minus 1 modulo n. We will call this set will be called z modulo n z. Okay? This set will be called z slash nz, which means z modulo nz. Why and why not, we'll see later why. Why do I have this notation? But this is the notation that you use for it. Now some books use this notation. Okay? Now, what's good about this set? What's really good about this set? It's finite, very good. First thing, finite set, very nice. I didn't think of that, but yeah, it's a finite set. Yeah. It contains all elements in Z. This is the set of equivalence classes. That's right. The set of all equivalence classes. It partitions the entire Z, and any element in Z, its equivalence class you can find in only one of these. That's very good. Also, what also can I do? I can turn this into a group. Okay? I can turn this into a group. Or before turning this into a group, I can define multiplication of these two. And I can define addition of these two. So what's 0 plus 1? The class of 0 plus the class of 1. What do you define it as? What's the natural way of defining this? 0 plus 1. 0 plus 1. So how do you define? You can define an addition on z mod n z. In addition on z mod n z. By saying, let's do a small example. Let's see what it should be. So mod 5, what are my possible classes? It's 0, 1, 2, 3, 4. And 4. Now, if you were to think, how do you define 1 plus 4 in this ring? In this set. How do you define 1 plus 4? 1 plus 4, how do you say? How do you reason? 1 plus 4 is 5, and 5 is 0. Okay? So you take 1, 5, plus 4, 5, and you define it to be the class of 1 plus 4, right? Which is the class of 5, which is the class of 0. Agree or not? That's what you do. So if you would say that 2 plus 4, what do you define it as?
6. 1,
6 is equal to?
1.
Are we good here?
Yeah.
So 2 plus 5, 2 plus 4, sorry, is equal to 6 is equal to 1. Oh wait, so 2 plus 4 is equal to 1, right? Okay, is it good? So how would you define, let's see, 1 plus 2? 3. You would define 1 plus 2 to be, it's just in a very, very natural way. Now this doesn't always work, but here we are lucky. If things are nice enough, it will work. Okay, let's try to define a multiplication. Can we define a multiplication? Could you say what is 2 times 3? 2 times 3, what would it be equal to? Let's define, oh man, let's define a multiplication. I mean, everything is nice right now, right? You can define a multiplication. Let's try to define a multiplication. Okay. So 3, 5 times 2, 5. What would that be equal to? You just take the class of 3 times 2. Agree or not? Which is the class of 6. Which is 1. How do you define 3 times 3? 3 times 3 is?
It's 4.
Is 9, which is? 4. Yeah. Things look very natural here, right? So the equivalence class of 3 mod 5 times the equivalence class of 3 mod 5. It's the equivalence class of 3 times 3 mod 5, which is the equivalence class of 4 mod 5. Okay, that's good. Now, there is a problem here. Immediately, when you do something like that, there should be something that comes out clear as a problem. Yes, sir?
What if it becomes 0?
You could do that, so 3 times 5. I'm not saying it's a group. I'm saying that you can define multiplication. Now there is immediately a problem that you should spot here. You could spot here. Yes?
Two numbers are not like an infinite number of numbers.
That's a very good point. So, I'm defining an addition on this set of equivalence classes. I'm saying 1 plus 4, the equivalence class of 1 plus the equivalence class of 4 is equal to the equivalence class of 5, right? Now, 1 is 1, we have that 1, we define it this way, is equal to 1 plus 4 is equal to 0 mod 5, right? Now, what is a function here? What is a binary operation? It's a function from the set times itself to the set. Now, in order for it to be a function, if I write 1 as 6, isn't it the same class? 1 and 6, aren't they in the same class, mod 5?
Yes.
And 4 and, let's say, I don't know, 4 and 24. Aren't they in the same class?
Yes.
4 and 24 mod 5 are in the same class. Agree or not?
Yeah.
Now here, wait a minute. The sum of 6 and 24 is 30. It's already different than 5 here. But is it a problem? Why? When you take mod 5, it goes away. It's still the class of 0 mod 5. Okay, so you have to show that your operation does not depend on the element that you choose to represent your class. So, if I put here, let's see, 16 plus, and I add, I don't know, let's say 29. What should I get? Without looking, what should I get? I should get 0, because this 16 mod 5 is equal to 1 mod 5. This 29 mod 5 is equal to 4 mod 5. So when I add them, I should get the same answer. Okay? Let's give an example where this doesn't work. Okay? Let's give an example where this doesn't work. Consider a function f from z mod nz, from the set of equivalent class to z. It's not a function. That sends the class of x modulo n to x. So it sends the equivalence class of 0 modulo n to 0. Okay? The equivalence class of n, where should it be sent? The equivalence class of n should be sent to n. Isn't that right? By this formula. But it also should be equal to 0. This is not a well-defined function. When you work with equivalence classes, you have to check every operation is a well-defined operation. Yes?
Isn't n not an element of z of the domain?
N? It's the class of n. It's not the number n.
Oh, right.
Right? The class of n is an element of the z mod n. It's equal to the class of 0.
Oh, okay.
Okay? Do you understand this? Is it clear? Yes, sir.
I don't understand the class of n under n is equal to n.
Okay, so I give you a function from z mod nz that sends the equivalence class of x to x itself. Okay? This looks normal, right? This looks like a normal and decent function. But here there's a problem. What is f of 0? Under this formula, what is f of 0? 0.
0.
Under this formula, what is f of n? The class of n. What is it? N. Well, wait a minute. Is the class of n equal to the class of 0? The class of n is equal to the class of 0. So these two should not do the same thing. This is not a well-defined function. We do another example of a function that is not well-defined. Is it clear? This is very important. I mean, I say this about everything. But, yeah. Is it clear? Is it clear why this is not well-defined? Okay? Are we good here? Any questions on this? This might come a bit, this well-defined thing might not be very easy to digest. That's what I want you to see, that you cannot just define functions on z mod nz. You cannot just do that. You have to check that they're well-defined. Okay. So maybe I'll just prove that addition is well-defined. I mean, we already proved it, right? Z mod n. Well, the addition from z mod nz to z mod nz is well-defined. So, how do you define the addition of two elements? We take xn plus yn, and you send it to the equivalence class of x plus y, of x plus y. This operation is well defined. Okay, now suppose I change the x. Suppose the class of x is equal to the class of a, and the class of y is equal to the class of b. I need to show that the class of a plus b is equal to the class of x plus y. Right? The class of a plus b is equal to the class of x plus y. A plus b, this replaces the x, this replaces the y, and to show that a plus b is equal to the class of a plus b is equal to the class of x plus y. Wait a minute. This is clear, right? The class of x is equal to the class of a implies that x is congruent to a mod n, right? It implies that x minus a is divisible by n. The class of y is equal to the class of b implies, or is equivalent to, the class of y. Hence, the class of x plus y mod n is equal to the class of a plus b mod n by the property we proved earlier. That if x is congruent to a and y is congruent to b, then x plus y is congruent to a plus b, and xy is equal to ab by the other property we proved earlier. Well, define addition and multiplication. Say n times xn times yn is xy. Okay? You can define the product of two elements, and that's a well-defined thing. If you change your numbers modulo n, you will get the same answer. Whereas in this function, if you change the representative of the class, you will not get a well-defined thing. Okay? Now in the assignment, I give you a function. In the one that I posted yesterday, or I posted yesterday, I give you a function from Zn to Z, and I ask you to check if it's well-defined or not. Okay? Great. So have a good weekend, everyone.
Okay, so I have two quick questions.
Yes.
We need to prove exercise 3.
Exercise 3. I mean, the proof of 1, 2, 3 is the same, right?
I mean,
1, 2, 3 are not the same. You can just do it. You can just say that. Oh, yeah. Yeah. Well, are they true for okay, sorry.
next question. So
Could you please stop the recording?
stop the recording.
Yeah.
How to do that? Yeah.